Okay, let me begin with the purpose of this research. Okay, the purpose of this research is the MHD dynamo, the understanding of the generation mechanism of the magnetic field in the Earth or other planets or stars. The goal is to understand the MHD dynamo process as a fundamental MHD process, physics process, especially by small, simple, and quick simulations. And this is rather contrast to the rather than the simulation of a real geomagnetic field by large and complex simulations. And actually, I have been doing this kind of large and complex simulations for many, many years, nearly 30 years now. And I have done various topics, and I'm happy to have this kind of topics. And especially among them, I have invented yin-yang grid in 2004. And this grid was for my large-scale, massively powered geodynamo simulations. And fortunately, this grid system is now used in several problems in geophysics. Not only geophysics, but also in astrophysics and solar physics and computational fluid dynamics, or even the image processing and so on. So I'm happy about that, but as you may know, this kind of large-scale simulation takes a lot of time and efforts, and it sometimes occupies almost all of the computer system, supercomputer systems. So it takes a lot of time, and it's not unusual to take a lot of more than months to get one result or one work. So I'm old now, so I'm not patient enough to get that kind of complexity. So in some sense, I'm fed up with this kind of complex, large-scale simulations. So now I'm into the simplicity. So the purpose is to understand the physics of MHD dynamo. And there are various approaches to fundamental process for MHD dynamo, like this one. And this is the approach I take today, simple simulation. And the key point of the simple dynamo simulation is the helicity. Flow helicity is the key for the dynamo. Helicity is the inner product of velocity and vorticity. And if the flow is in the winding or helical flow, this has a helicity. If in the right-hand winding, it is a positive helicity, and if this is left-hand winding, this is a negative helicity. So helicity is very important, and because it twists and stretches the magnetic field lines to amplify the field energy. And realization of the helical flow is a challenge, especially in dynamo experiments. They are trying to put many efforts to realize the sufficiently high helicity by the experiments, by using liquid metal or plasma, so on. And in nature, in a rotating system, the helicity naturally appears because of the Coriolis force. And in my old research, I have pointed out that helicity, helical flow, this kind of helical flow plays an important or key role in generating the dipole field. So helicity is important. And the purpose is a simple simulation, but need a helicity. But of course, if you have a rotation, you will have the helicity, but do we need the rotation or omega? The rotation is always a problem for numerical simulations because rotation means the very thin Ekman layer. You need to have some fine grid meshes to resolve this kind of a thin layer. So it would be nice if there is some kind of a very simple laminar convection system with no rotation. But in standard configuration of the thermal convection system like a cube or cylinder, there's no strong helicity and there's no dynamo. So I came up with this kind of a thinking. What if we place a cube like this way? And it feels like that this kind of convection in this slanted cube may have some kind of helicity, that it's still a little bit complex. So this is how I came up with the idea of this tetrahedral convection system. We place a regular tetrahedron in such a way that the two oppositely edges are placed in the horizontal plane. And we put the heat from the bottom. Then convection, the thermal convection naturalizes, and it will, or I hoped, have some kind of helicity. And of course, if we increase the Rayleigh number, the flow becomes turbulent. But the focus on this work is the simplicity. So I focus on the laminar flow or low Rayleigh number regime. So the questions are, what is the flow pattern in this kind of a simple configuration? And does it have convection cells, or does it have helicity? That's an important point. And does it work as an MHD dynamo? So this is the model. We think about a regular tetrahedron in this XYZ plane. And this edge is in the XY plane. This edge is also parallel to the XY plane. And we think about an MHD fluid confined in this regular tetrahedron region. And we solve the MHD equations in the simple XYZ coordinate system. And as for the simulation model, we have to solve the MHD equation somehow, but because I want a very simple methods, so I use the very simple central difference method with the same grid spacing in X, Y, and Z directions. So it's a very uniform grid system. This is the simplest grid structure. And as for the time integration, we use the standard Runge-Kutta integration scheme. Of course, there is some kind of a question how to solve the tetrahedral region, the fluid inside of this slanted boundaries with that kind of a uniform grid system. Of course, there are some kind of sophisticated methods, such as immersed boundary method, popularly used in CFD community, or you can make some kind of refined grids near the boundaries, but it's not simple. So, however, let me start by the two-dimensional analog. In 2D, we can place this kind of a right triangle in such a way that all the vertex and edge or sides are just on the grid points. So we can solve the second order finite difference method on this grid for this slanted diagonal borders with no special care about the boundaries. So this is just a standard central difference method. And this was a 2D case, and this is also true for 3D case for tetrahedron. We can place the regular tetrahedron in such a way that all the vertices or edges and surfaces are just on the grid points. So in this case, we do not need no special care about the treatment of the boundaries. All we have to do is just to solve the second order finite difference method. And in this work, I use just a 80 cubed grid points. It's very small. Even I can run this simulation code on my PC. And as for the boundary condition, we solve the velocity inside of the green regular tetrahedron. The flow is zero, exactly zero on the surfaces. As for the magnetic field, it can go out to the tetrahedron, go out to the outer space, and we solve the diffusion equation of the magnetic field. And we set the outer cube, the red one, outside of the regular tetrahedron, and we assume the periodic boundary condition for this red outer cube. As for the initial condition, we assume the so-called polytropic state with these parameters, and this parameter means the density contrast between the top and bottom of the tetrahedron is very small, so it's almost no stratification. So we can ignore the stratification effect or compressibility effect. And in the initial condition, there's no flow but unstable when we put the sufficiently high temperature gradient. And we put random perturbation to pressure with tiny seed magnetic field. And this seed field will be amplified if the dynamo is operating in this system. These are the physical parameters. Of course, simulation can be applied for any scales, but to make my images as concrete as possible, I think about this kind of concrete data. I think about the edge length of the tetrahedron of square root 2 meters, 1.4 meters. The density is this one, temperature and this one, and viscosity is this one. So the viscous diffusion time for this tetrahedron's height is about 1.6 seconds. Prandtl number is 1, magnetic Prandtl number is 5, and the gravity acceleration is very high in order to induce the convection. So this is a kind of artificial setting for the artificial or virtual MHD fluid for this convection system. Now let me move on to the simulation results. This is time developments of energies. This is time and energies. And these dashed lines denote the flow energies or convection flow energies. After the starting of the convection, it soon gets to the saturated state. And this green one shows the total magnetic energy inside of the cube. And this blue one shows the energy inside of the tetrahedron because the magnetic field can diffuse out to the tetrahedron. So this energy is comparable to the convection energy. If we change the parameters, I sometimes get the larger energies. The magnetic energy can become larger than the flow energy. So anyway, this energy is sufficiently strong. We can say that the dynamo is operating, is acting. And let me show the simulation results in the final state, in the saturated state. To show the 2D cross sections, before I show the slices, let me point out that all slice planes parallel to in the XY plane is always rectangle. If we cut the regular tetrahedron in this direction, we always get this kind of regular triangle rectangles. So this is the upper cross section. These are middle cross section. This is lower cross sections. And this is velocity, Vz and Vx and y. This is vertical component. And this is horizontal components. So one thing we notice is that these flows are very symmetric. And these are the streamlines of the velocity field. Actually, I have drawn a lot of many streamlines to understand the structure, three-dimensional structure of this velocity field. And this is one of the symmetric configuration of the streamlines. And let me show the three-dimensional view of the structure of these streamlines. I will briefly explain how we get this kind of visualization. So anyway, we notice that the streamlines are very symmetric. And one important feature of these streamlines is that it is confined. The streamlines is always confined in one of the segment or quadrant in regular tetrahedron. PQSR. So this is a quarter of regular tetrahedron. And streamlines are always confined in this tetrahedron, PQRS. So we can say this is a convection cell, and there are 4 convection cells, and they are symmetric in horizontal direction. Okay. So there are 2 kinds of symmetries for this convection structure. One is reflection symmetry about this plane, and the other is another reflection symmetry about this plane. So we have 2 reflection planes or symmetries in this configuration. Configuration of the velocity field in horizontal direction. And in addition to that, it took some time to notice for me to notice that there is another symmetry of this velocity field. It's a vertical symmetry. If we rotate, here we have an x-axis in this direction, going through the midpoint of this edge in horizontal direction. If we rotate this convection cell for 180 degrees, we get exactly the same configuration. PQSR becomes SRPQ. And the configuration is the same. And the flow inside of this cell is exactly the same. So the velocity is symmetric about the rotational transformation about the x-axis. There's another one more symmetry about the rotation about the y-axis too. So the combination of the 2 horizontal symmetries and the 2 vertical symmetries of rotations, we get there are various compositions of these transformations or symmetries, and I have noticed that this symmetry, all of them forms a set of group 4, B4, dihedral group of order 8. So there are 8 components of the symmetries, all for this velocity field. And as for the magnetic field, it also has a very highly symmetric structure. And I do not have time to explain the detail, but the magnetic field has also the dihedral group symmetry. And these are the visualization of the magnetic field, green one, and the floral field or streamlines, blue one. And let me show the structure of these fields. So they are combined in very intriguing way, and they are very symmetric. And this is a schematic summary of the 2 fields. The flow is basically confined in one cell, and this one cell or quadrant have a rotation symmetry about in the vertical direction. The magnetic field has also, the structure of the symmetry is different. The transformation is different, but the magnetic field has some similar kind of symmetry, the same number of symmetries. And the structure of the magnetic field is summarized like this one. And this schematic diagram also explains how the magnetic fields are generated. There's some ascending flow along this midline. And because of this flow, there's some kind of 2 opposite flows going away from each other, like this one. And this ascending flow stretches the magnetic field lines against the field tension force, because the magnetic field has always a tension force like the rubber band. And against the rubber band tension force, the flow does some kind of work against the tension force. This is how the magnetic field energy is generated. And if we focus on this part, these lines, these flows, opposite flows, are stretching the magnetic field lines. And it's known that stretching the field lines always amplifies the magnetic field. So there are two kinds of generation mechanism of the magnetic field in this configuration. Of course, there's some kind that's exactly the same structure in these edges too. So this is how the magnetic field is generated and sustained in this convection system. Now let me move on to the visualization methods in this work. All the visualizations I have shown so far are in situ visualization. In situ visualizations mean the applied visualization in the computation time. There's no post-process. I do not do post-process anymore. So I always apply the visualization during the simulation time, and the simulation results for me means that the images or movie files. And of course, if you apply the in situ visualization methods, the problem is always the interactivity. You cannot observe the simulation phenomena from, say, different angles if you do not place the visualization camera at this point. In order to resolve this lack of interactivity of in situ visualization, I have proposed some years ago 4D street view method. The key idea of the 4D street view is place many cameras inside of the simulation region. I scatter many simulation cameras and apply the in situ visualization from all of them. And the output is a lot of movie files, and we apply some kind of interactive analysis for these movie files, like a Google Street View. So this is the key idea of the 4D Street View, and this is how I analyze this field. I placed many cameras along a line, and because the camera is these cameras are the so-called omnidirectional cameras, so I can change the direction of this is omnidirectional movie file, so we can change the direction by just kind of a mouse drag motion by changing the motion. And if we click the keyboard, I can change the camera position. That makes me to feel like move along the lines and so on. So this is how I interactively analyze the simulation data for this work. As for the 2D slice visualizations, I use the SVG library. SVG stands for the Scalar Vector Graphics format. It's a standard one for vector graphics. Vector images means that it is opposite of the raster images. Raster image is the usual one. Raster one is some kind of a set of pixels, but vectors are not a set of pixels. They are kind of mathematically defined images. Because there's no scale for the vector images, we can change the scales from smartphone to web browsers. This is the reason why SVG is very popular these days, because many people are using the same images from PC or smartphones. So that browser size is very different, but SVG can handle this kind of scale changes automatically. So I have, this is the features of SVG. It has some kind of a drawing features, polygons, curves, and so on, text, coordinate transformations, and some kind of grouping, and even simple animation is included in the definition of the SVG. So the SVG, one of the good things about SVG is it's a text data, so we can easily edit or make the SVG format directly. For example, this kind of a vector arrows, glyphs are generated by this one simple images, and they are copied many times. And I have developed a library for 2D visualizations with SVG, and it's publicly available at GitHub. So if you are interested in that, please try it and use it. And I have implemented the standard visualization method that is necessary for simulation data analysis, such as vector glyphs. But this vector glyphs has animations, very simple animation feature. And I like this kind of animation feature. It's very effective. You can try this site. You can check how this simple animation can convey very good images about the vector field. It's very different from the still images. And there's also a very simple contours. And this is one of the reasons why I started to develop this tool, because in the this tetrahedral dynamo model, I have this kind of diagonal borders, and I wanted to draw the contour lines with these diagonal borders. And the contours are usually written by the so-called marching squares algorithm. It's a standard algorithm, so used for many years. But the standard marching squares algorithm cannot apply this kind of diagonal borders. So I invented this kind of new algorithm to draw the contours. And the good point about SVG is that you can feel the colors inside of the curves. So we can easily show this kind of field contours by SVG. But anyway, please try this SVG library. So this is summary of my talk today. I proposed the tetrahedral dynamo model, and it's a simple laminar rotation-less convection system that works as a dynamo. And there's no rotation, there's no Ekman layer, so there's no hassle for high resolution. This is a very good point for quick simulation. And there's no rotation, but it has still helicity. And this is the reason why we have dynamo. And the model is numerically simple too. We can solve this MHD equation in this regular tetrahedron with even the uniform XYZ coordinate system with no special care about the boundaries. And because of the configuration is symmetric, the results is also symmetric. I mean, the results, the field and flow and magnetic fields, both of them are very highly symmetric structure. And this highly symmetric structure makes me to analyze the data very easily. And we apply the house-made visualization method to obtain these results. So that is, thank you very much.